In this video, we're going to talk about z-scores. But before we talk about z-scores, let's talk about measures of position. So measure position describes the relative position of a certain data value within the entire data set. So now let's talk about z-score. This represents the distance that a data value is from the mean in terms of the number of standard deviations. So the population z-score and the sample z-score is pretty much the same formula. It's the data value minus the mean divided by the standard deviation. So the z-score has no unit of measurement. It has a mean of 0 and a standard deviation of 1. So why do we use z-scores? This compares two different things by having the same mean of 0 and a standard deviation of 1. In other words, instead of trying to compare apples to oranges, we're trying to set it up so that we can compare apples to apples. So what does a z-score mean? If you have a z-score of 1 in 2500ths, this means that the data value is 1 in 2500ths standard deviations above the mean. If you have a z-score of negative 2 in 2/10ths, this means that the data value is 2 in 2/10ths standard deviations below the mean. Okay? And we will always round z-scores to 2 decimal places. Okay, let's take a look at a couple of examples. So the highest batting average ever recorded in Major League Baseball was by Ted Williams in 1941 when he hit .406. That year, the mean and standard deviation for the batting average is given. In 2014, Jose Altuve was the American League batting champion, batting average of a .341. In 2014, the mean and standard deviation for batting averages are given. Who had the better year relative to his peers, Williams or Altuve, and why? So we're trying to compare two different eras of baseball to one. This is where we're going to use a z-score. So let's start with Ted Williams. So again, the formula is going to be what? The data value minus the mean divided by the standard deviation. Okay, so plug in. His batting average was .406. The mean was this. And the standard deviation is this. So when you subtract and divide, rounding to 2 decimal places, we get approximately 3 8200ths. Now, let's do Jose Altuve. So again, data value minus the mean divided by the standard deviation. Well, his batting average was .341. The mean, which is given, divided by the standard deviation. So if you subtract first and then divide, you get approximately 2 5900ths. Right? Well, whose z-score is higher, Ted Williams or Jose Altuve? Well, clearly that is going to be Ted Williams. That is a higher z-score than Jose Altuve's. So Ted Williams had the better year. So let me write this out for you now. So Ted Williams had the better year since his z-score is greater than Jose Altuve's. Okay, let's take a look at the next example. So pizza parlor franchise specifies that the average mean amount of cheese on a large pizza should be 8 ounces with a standard deviation of 0.5 of an ounce. An inspector picks out a large pizza at random in one of the pizza parlors and finds that it's made of 6 9/10 ounces of cheese. Assume that the amount of cheese is below the mean by more than 3 standard deviations. The parlor will be in danger of closing its franchise. Is the pizza parlor in danger of closing its franchise? So here we'll use the z-score. So again, the z-score is equal to what? The data value minus the mean divided by the standard deviation. So in this case, the data value is 6 9/10. The mean that was specified is 8. Standard deviation is going to be 0.5 of an ounce. Subtract and then divide, that's negative 2 2000ths. Again, remember, I'm going to round all z values to 2 decimal places. So, is this 3 standard deviations below the mean? In this case, it's not. So it doesn't look like the pizza parlor is in danger of losing its franchise. Let me write this out now. So no, since the z-score is not less than 3 standard deviations below the mean. Okay, one other example we're going to take a look at. So babies born after a gestation period of 32 to 35 weeks have a mean weight of 2,600 grams and a standard deviation of 660 grams. Babies born after a gestation period of 40 weeks have a mean weight of 3,500 grams and a standard deviation of 470. Suppose a 34-week gestation period baby weighs 2,400 grams and 40-week gestation period baby weighs 3,300 grams. Which baby weighs less relative to its gestation period? Why? So again, we're trying to compare apples to oranges right now. With a z-score, we want to be able to compare it apples to apples. All right, so let's start with 32 to 35 weeks first. Z-score, data value minus the mean divided by the standard deviation. So in this case, that's going to be what? 2,400. The mean is 2,600. Standard deviation is 660. So rounding to 2 decimal places, that's this. Now let's do after 40 weeks. So again, z-score is the data value minus the mean divided by the standard deviation. So this time it's 3,300 minus the mean divided by the standard deviation. To 2 decimal places, that ends up being this. So which baby weighs less? Well, remember, we're dealing with negative numbers, so which of those decimals is less than the other? Well, it's clearly negative 43 hundredths is less than negative 30 hundredths, so the 40-week gestation period baby weighs less. So let me write that out now. The 40-week gestation period baby weighs less than the 34-week gestation period baby, since the z-score of negative 43 hundredths is less than the z-score of negative 0.30. In this video, we're going to be working on the 5-number summary and outliers. So the 5-number summary is 5 data values that include the minimum data value, the first quartile, the median, the third quartile, and the maximum data value. So let's take a look at an example. So a group of Brigham Young University, Idaho students collected data on the speed of vehicles traveling through a construction zone on a state highway, where the posted speed was 25 miles an hour. The recorded speed of 14 randomly selected vehicles is given below. So determine the quartiles, interpret what they mean in the context of the problem, and write out the 5-number summary. So first off, I need to write these numbers out from least to greatest. So when we do that, we get this. Now, at this particular stage, I would start with the middle and figure out what the median is going to be. Since we have 14 randomly selected vehicles, we know we're going to have 2 different values to look at. So the 2 middle values are going to be 32 and 33. So what do? We add them up and divide by 2. Now, for the first quartile, we look at the lower half of the lower set of numbers, which I boxed here, and now find the median. Well, in this case, that's going to be 28. And then for the third quartile, we look at the higher data values, half of them. I've highlighted that in blue. And here that is 38. Okay? So now what I'm going to do is I will write out in the context of the problem what each of these mean. We'll start with the first quartile. Remember, that separates the bottom 25% from the top. So here's how we would write this out with respect to the context of this problem. 25% of the speeds of vehicles traveling through a construction zone are less than or equal to 28 miles per hour. Now, for the median, it separates the bottom 50% from the top. So it's going to be exactly the same thing, except for the 25%, it's going to be 50%. So here's how you would write this out. 50% of the speeds of vehicles traveling through a construction zone are less than or equal to 32 and 5/10 miles per hour. Now, the third quartile, that separates the bottom 75% from the top. So here's how we would write this out. So 75% of the speeds of vehicles traveling through a construction zone are less than or equal to 38 miles per hour. Okay, a 5-number summary then. So we would start with the least data value. That's going to be 20, up with the unit of measurement. The first quartile, the median, the third quartile, and the largest data value. There's my 5-number summary. Okay, let's take a look at the next example. The following data represent the miles per gallon of a random sample of smart cars with 3-cylinder and 1-liter engines. Write out the 5-number summary. Now, in this particular case, the data is already listed from least to greatest. So we have 24 data values, so the 2 middle values are going to be here and here. So again, I would start with the median, add the 2 numbers, and divide by 2. That's going to give me this. Now, for the first quartile, we'll be looking at these particular values. So here again, we have 2 different values that we're going to have to take a look at. Here and here. So Q1, add the 2 values, and divide by 2. That gives me this. And the third quartile, we'll be looking at these data values. And again, there's an even number, so we're going to have 2 again, those 2. And that gives me 41. Okay, so let's write out the 5-number summary. The least data value, 31 5/10. I'll put the unit of measurement. The first quartile, the median, the third quartile, and the greatest data value in the set. There's my 5-number summary. Okay, before we talk about outliers, let's talk about the interquartile range. That is the range of the middle 50% of the observations in a data set. So let's determine the IQR for the previous example and write out what it means in the context of the problem. So we know IQR is Q3 minus Q1. Well, we know that's 41 minus 36 and 85 hundredths. And that is going to be 4 and 15 hundredths. Don't forget your unit of measurement. Right. Okay, so I'm going to write out what it means in the context of the problem now. So the range of the middle 50% of the miles per gallon in the data set is 4 and 15 hundredths mpg. As a note, the more spread the data has, the higher the IQR is going to be. Okay, when I talk about describing the distribution, I refer to describing the shape of the graph, its center, and its spread. So if the shape of the distribution is symmetric, I want to be able to use the mean and the standard deviation. If it's either skewed left or skewed right, we'll use the median instead of the mean and the interquartile range, IQR, rather than the standard deviation. Okay, next I want to talk about an outlier. This is an extreme, high or low data observation in a data set. So outliers distort both the mean and standard deviation because neither is resistant. Because these measures are often the form of basis of most statistical inferences, any conclusions drawn from a set of data that contains outliers could be flawed. So we need to be able to check for outliers, and here's how we're going to do this using the quartiles. Number 1, we want to determine the first and third quartiles of the data. Number 2, compute the interquartile range, or the IQR. Then determine the fences. The fences serve as a cutoff point for determining values. So I have our lower fence formula and our upper fence. If an observation is less than the lower fence or a data value is greater than the upper fence, then it is considered an outlier. Okay, so let's take a look at a couple of examples. Let's start with the speeding. So I've already written out here that the third quartile is 38 and the first quartile is 28. So first off, let's identify the IQR. That's Q3 minus Q1. That is 38 minus 28. That is 10. Okay, now let's do the lower fence. Well, that formula is Q1 minus 1 5/10 IQR. Q1 is 28. We know the IQR is 10. That's 28 minus 15, and that is 13. The upper fence, that's going to be Q3 plus 1 5/10 IQR. So we know Q3 is 28. Again, IQR is 10. So, in the data set, we would look for a data value that is less than 13 or a data value that's greater than 43. Let's go back to the data set quickly and take a look. So here's the data set. Do we have a data value that is less than 13? No, the least value is 20. Do we have a data value that is greater than 53? That's no, because the largest data value here is 40. So we can conclude that there are going to be no outliers. So let me go back to the page and write that out. There are no outliers since there is no data value that's greater than 43, which is the upper fence, or any data value less than 13, which is the lower fence. Okay, let's take a look at the other example then. So again, we have the third quartile as 41 and the first as 36 at 8,500. So quickly, let's do the IQR. All right, so let's now do the lower fence. So we know that's 36 and 8,500 minus 1 5/10, 4 and 1,500. When you multiply and subtract, you get this. And the upper fence, okay, so Q3, that's 41. Again, IQR. When we multiply and then add, we get this. Okay, so we're looking for a data value that is less than 30.625 or a data value that's greater than 47.225. So let's go back to the data set and take a quick look. Okay, so here's the data set then. So there is no data value less than 30.625 because the least data value is 31 5/10. But we do have a data value that's greater than 47.225, and that's this data value of 47 5/10. So 47 5/10 is our outlier in this problem. So let's go write that on the paper now. So 47 5/10 is an outlier since that particular value is greater than 47.225, which is our upper fence.